Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Ferromagnetism from the paper Functional Materials. The main points which will be covered in this module are: first, we will be discussing about the ferromagnetism. Second, the domain movement in ferromagnetic materials. Third, the domain wall structure in ferromagnetic materials. Lastly, we will be discussing about the molecular field theory for a ferromagnet. So students, let us start with a brief introduction. Ferromagnetic materials are the most important of all the magnetic materials due to their excellent magnetic properties. They possess large magnetic susceptibility and hence large magnetic moments. Based on their behavior in the magnetic field, they are used in a variety of applications, starting from the transformer cores to the data storage devices. In this following sections, we will discuss firstly the basic characteristics of these materials, followed by the fundamental basis of ferromagnetism. Ferromagnetic materials. In addition to permanent magnetic moments as contained in paramagnetic materials, ferromagnetic materials consist of ordered regions or domains of single orientation of magnetic moment, giving rise to large finite magnetization in the absence of a magnetic field. This is much like similar to the polarization in ferroelectric materials. This phenomenon is observed below a critical temperature called as Curie's temperature, above which the material behaves like a paramagnetic material. As we can see from the figure, that is, with no applied magnetic field, some of the dipoles are aligned, leading to a large magnetic moment. Now, with the application of the applied magnetic field, there are better aligned dipoles leading to large induced moment. And this alignment is due to the exchange interaction for aligned moments. When a ferromagnetic material is subjected to varying magnetic field, it exhibits a ferroelectric-like hysteresis loop between the magnetization and magnetic field. A typical ferroelectric loop, which ferromagnetic materials also exhibit, is shown in the figure, where M is the magnetization and H is the applied magnetic field. Most of the ferromagnetic materials are elemental metals such as iron, nickel, cobalt, etc. However, some oxides such as chromium oxide are ferromagnetic oxides. These oxides also tend to be conducting and behave like metals. Now here there is a parameter which is the saturation magnetization, and it has been tabulated here for all these ferromagnetic metals. ferromagnetic materials. Now, the ferromagnetic hysteresis loop, as shown in the figure, is due to the domain movement in ferromagnetic materials. The spontaneous magnetization is not apparent in the materials which are in virgin state or have not been exposed to the magnetic field, which is represented by the point O in the figure. This is again similar to the case of ferroelectrics because these materials also contain the domains which are randomly oriented in a virgin material. Upon the application of magnetic field, these domains start aligning in the direction of applied magnetic field, which is represented by point B in the figure, and when completely aligned give rise to saturation magnetization, that is MS at point B, and there is minus MS in the opposite direction. The domain growth in ferromagnetic materials occurs by the growth of domains whose magnetic moment is favorably oriented with respect to the field. These domains grow at the expense of unfavorably oriented domains. This very much in contrast to the mechanisms in ferroelectric materials where favorably oriented domains first nucleate and then grow. When the field is reduced to zero, which is represented by point C, the domains do not revert back to their original configuration in the virgin state. Rather, they adopt a configuration so that there is a net magnetization in the absence of field called as remnant magnetization, which is represented by Mr in the graph and minus Mr in the opposite direction. To bring the magnetization of the material back to zero, one needs to apply an extra field in the opposite direction, which is called as coercive field, and it is represented by minus Hc and plus Hc in the opposite direction. A ferromagnetic material is a hard magnet when it has large coercivity, or soft magnet when coercivity is small. Often magnetic hysteresis loops are also represented as BH curves where B is magnetic induction, B is equal to mu naught H plus M, or it is equal to mu naught mu R H, where H is the applied magnetic field. Hence, the equivalent points in a BH curve would be BS, the saturation induction, and BR, the magnetic remanence. As evident from the figure that this circled part has been zoomed, which gives us the variation from the point O to B through A. Another feature which is used to explain hard and soft magnets is the area of BH or MH curve, which represents the power dissipated as heat, and it can be expressed as power dissipated is equal to the area of BH curve multiplied by the volume of the material multiplied by the frequency. So, since a hysteresis curve implies loss of certain amount of energy, typically soft magnets show lower energy losses as compared to hard magnets. Soft magnets with reasonably large MR and smaller HC are useful for transformer and motor cores, where energy dissipation due to AC fields is low, while hard magnets are useful as permanent magnets and magnetic memories. As it is clear from the figure that the BH curve, which is represented by the first figure, where it has a large M and HC desirable for permanent magnets and magnetic recording and memory devices. It retains a large fraction of saturation field when driving field is removed. The second graph shows that the area of the hysteresis loop is smaller than that of the previous graph, and it is related to the amount of energy dissipation upon the reversal of the field. The third graph is the narrow hysteresis loop that is having smaller energy dissipation. It is desirable for transformer and motor cores to minimize the energy dissipation with the alternating fields associated with AC electrical applications. This figure shows the formation of domains in a ferromagnetic material. As we can see from the figure that the flux lines on the surface of a magnet in monodomain state represents large demagnetization energy. This leads to increase in the number of domain and the decreasing the flux lines on the surface. Again, the formation of domains and their size in these materials is basically due to balance between various kinds of energies associated. First is the exchange energy, which makes the magnetic moments align in one direction without violating the Pauli's exclusion principle. Second is the magnetostatic energy in response to the flux lines at the surface of the material in the monodomain state, which increases as alignment increases, or in other words, high surface magnetic charges. Third is the magnetocrystalline or anisotropy energy, which is due to the coupling between the spins and the crystal lattice or spin-orbit coupling. It is dependent on the crystal structure governing the direction of magnetic moment orientation, as there are some crystallographic directions along which sample is easy to magnetize than others, such as for most cubic materials, that is square bracket 111 is the easy axis except for those containing cobalt, which have 100 as the easy axis. As a consequence, hard and easy directions have different coercivities. Lastly is the magnetoelastic energy, which is due to the changes in the lattice parameters of the material as a result of spin-orbit coupling. The phenomenon is called as magnetostriction, and it is quite useful from application point of view. Typically, monodomain state increases the magnetostatic energy significantly which is decreased by the formation of domains. Although existence of multi-domain state also requires a surface energy, the phenomenon is energetically stable. In ferromagnetic materials, not only atoms possess the permanent magnetic moment, these magnetic moments are also aligned along certain directions in an ordered fashion in regions called as domains. That is why ferromagnetic material gives to a large non-zero magnetization even in the absence of magnetic field. The domain movement in magnetic materials can be greatly affected by the defects which can pin the domain wall and hinder its moment. Since the interaction of domain walls with defects affects the behavior of magnetic moments or magnetic materials, we will now study how does a domain wall is formed, which is leading to the domain reversal, and this domain reversal is leading to the hysteresis loop. A domain wall is often called as the Bloch wall, which is termed after F. Bloch in 1932, proved that the magnetization cannot change discontinuously at a domain boundary. A Bloch wall defines a region between two neighboring domains where the spin moments change gradually from one orientation to another, as shown in the figure in case of 180-degree or anti-parallel domains. Bloch walls can be 10 to 100 nanometer in width and can have an energy of the order of 10 to the power minus 4 to 10 multiplied by 10 to the power minus 4 joules per meter square. As we have mentioned above, since domains of favorable orientation with respect to the applied field grow at the expense of unfavorably oriented domains, the Bloch wall also moves towards the left, as shown in the figure. Microscopic reasons of ferromagnetism. Derivation of the Curie's law assumed that the localized atomic magnetic moments do not interact with each other at all. They are just reoriented by the applied magnetic field. Weiss explained the observed Curie-Weiss behavior by postulating the existence of an internal interaction between the localized moments, which he called a molecular field. He did not speculate as to the origin of this molecular field, beyond suggesting that it is a mutual interaction between the electrons which tends to align the dipole moments parallel to each other. We can't really criticize Weiss for this. Remember that the electron had been discovered only 10 years earlier and the quantum mechanics hadn't been invented yet. The Weiss molecular theory. The intensity of the molecular field, that is HW, is directly proportional to the magnetization, and hence this HW is expressed as the product of magnetization with a molecular field constant gamma, which is a characteristic of the material. Hence, the internal field, or we can say The total field which is acting on the material is the summation of H plus HW. Now we can put the value of HW, then the H total will become H plus gamma M. Now, for a ferromagnetic material, we need to replace H with H total, and hence this susceptibility, which is equal to M by H, or it is equal to C by T. Here we will put the value of H as H total. Hence, M by H plus gamma M will be equal to C by T. This implies that M is equal to C multiplied by H divided by T minus gamma C. So finally, we will get the ratio of M by H is equal to C by T minus theta, where theta is equal to gamma C and it has a unit of temperature and is called as the Curie temperature. This is also called as the Curie-Weiss law. The temperature dependence of magnetization or susceptibility. The figure shows that while Ms starts dropping at T equal to Tc, the ferromagnetic transition temperature, and then it dies off slowly until a temperature theta, which is the paramagnetic transition temperature. Now, there is a divergence in susceptibility inverse at T is equal to theta in the paramagnetic region, which is a signature of a phase transition to a magnetically ordered phase with spontaneous magnetization. Hence, if one observes a positive value of theta, it indicates that molecular field is along the same direction as applied field, and hence it facilitates the parallel alignment of magnetic moments to each other, as should be the case with a ferromagnetic material. So students, let us discuss what are the implications of this Curie-Weiss law. At Tc, the interaction energy, that is mu b Hw, must be approximately equal to the thermal energy, which is Kb Tc. So for a material with a Curie temperature of around 1000 Kelvin, the Hw will be equal to 10 to the power 3 oersted, and this is a very large field. Exchange energy. Students, let me mention here that the origin of Weiss molecular field is the exchange interaction as a combined consequence of the Pauli's exclusion principle as well as the Coulombic interactions between the electrons. For instance, in case of two electrons, they can arrange themselves parallel or anti-parallel. If parallel, Pauli's exclusion principle requires them to remain far apart, and if anti-parallel, the electrons may come closer together and their wave functions overlap considerably. Hence, the electrostatic energy of the electron system is governed by the relative orientation of the spins with respect to each other, either, and the difference in the energy is a manifestation of the exchange energy. For transition element materials like iron, nickel, and cobalt, the exchange energy is minimum for parallel spin configuration, while for certain other materials like manganese oxide and various other ferrites, exchange energy is minimum when the spins are arranged in anti-parallel fashion, and these materials are called as antiferromagnet or ferrimagnetic material. The exchange interaction is a short-range interaction, and hence only the nearest neighbor atoms produce the molecular field. The magnitude of exchange or molecular field can be worked out by equating the exchange energy, that is mu b HW, with thermal energy kT at Tc, that is HW is equal to kTc by mu b, which turns out to be the order of 1 kilotesla. And as we have previously mentioned that this is a very large field. In terms of quantum mechanics, we can write Heisenberg Hamiltonian as H exchange is equal to minus summation over Ij, J exchange Si multiplied by Sj, where J exchange is equal to the integral over phi a star as a function of r1, phi b star as a function of r2, this whole multiplied by bracket 1 by rab plus 1 by r12 minus 1 by ra1 minus 1 by ra2 bracket close, multiplied by phi b r1 phi a r2 dr1 dr2. J is being positive implies that Si and Sj are parallel, that is, material is ferromagnetic. For example, as we can see from the figure, for iron and nickel and cobalt. On the other hand, a negative value of J implies anti-ferromagnetic ordering. As we can see from the figure, the materials like chromium and manganese. The figure is a Bethe-Slater curve which shows the plot between J versus the ratio of the radius of atom and the radius of 3D shell. So students, let us summarize what we have learned in this module. First, the ferromagnetism is one of the most practically useful phenomenon. Second, ferromagnetism arises from the ordering of spins which is aligned in one direction, leading to a finite large magnetic moment even at zero fields, and hence large and positive magnetic susceptibility. Further, ferromagnetic materials are defined as hard or soft magnets determined by the area of BH curve and the coercivity. The phenomena of magnetic switching involves the motion of domains, region of uniform magnetization. Ferromagnetic materials also exhibit the Curie-Weiss behavior. Upon heating or cooling, they transform into a paramagnetic state at Curie's temperature or Tc upon heating. Thank you.